Okay, so welcome to the seminar today. And today we have Hartnoll from Cambridge telling us about something about quantum Hall matrix models and emergence of space from such simple matrix models. Okay, over to you, Son.
Great, thanks a lot for the invitation, and apologies for being a couple minutes late. So, right, I'm going to talk about entanglement in the quantum Hall matrix model. I'll define everything as I go along, and please feel free to ask questions as I go. Feel free to interrupt, because that'll be helpful. All right, so let me just start very briefly with some big picture motivation, probably familiar to many of you. So many beautiful things happened in physics in the last century. In theoretical physics, something nice that happened near the end of last century was that Strominger and Waffer gave a microscopic understanding of black hole entropy in some special cases. But for my purposes, one thing that's interesting about that is a connection between geometry, where the entropy is the area of a certain special surface in spacetime, and a counting problem, which is a microscopic counting of the entropy. So there's a correspondence between geometry and counting. And so again, the area is this Bekenstein-Hawking area of the horizon. And the counting problem turned out to be essentially the following. It's of course, some very highly supersymmetric thing, but in essence, what you end up counting is you imagine a string. The string is carrying waves, quantized waves along it, and the string carries a total momentum p. That's the momentum in the string. And of course, this momentum could be carried in lots of ways. There could be 10 quanta with momentum 1, or there could be 2 quanta with momentum 5. And those are 2 different ways of carrying a total momentum 10, right? And so the entropy is the number of ways that the string can carry this momentum. And that's D. And this is called a partition. And so what Strominger and Waffer used was the famous formula from Hardy and Ramanujan that gives you the asymptotic behavior of partitions for large P. And so you take this formula for the partitions, you plug it into here, and you get the corresponding an area in space-time. Okay, and so let's just keep that in the back of your mind, and we'll return to it in 45 minutes or so, hopefully. Okay, now something that happened recently, more in the last 10 years or so, is that this understanding that there were certain counting problems associated to geometry was extended away from black hole horizons. And this is the Ryutake-Nagy formula for the entanglement. And so the idea here is that if you consider a minimal surface, you split spacetime, you partition spacetime with a minimal surface, so that's what these soap bubbles are representing, then the entanglement across this surface, right? So you've got spacetime, you split it with some minimal surface, and you ask about I'm going to define entanglement for you in a couple of minutes. The entanglement across this surface, well, there's a sort of obvious contribution that whatever fields you might have in your spacetime will be entangled. But in addition, there's a universal gravitational contribution, which is the area of the surface over 4g Newton. So very much, so Bekenstein-Hawking entropy can be understood as a special case of this. And so now this associates some kind of entropy to more general regions of space. And you could ask, what is the microscopic bulk origin of this entanglement? Analogously to saying that, well, the black hole entropy is counting certain string states or something. And if we could answer this question, we will certainly learn that it suggests that if we can understand this, we'll learn something universal about the quantum state that underlies semi-classical space-time. Okay, so space-time is in some quantum state of space itself, if you like. And if we can understand the entanglement in that state, we would actually understand how is space-time actually made. So this talk can be thought of as some baby steps in the direction of understanding where these kind of entanglement terms might come from microscopically. So I've talked about entanglement. Let me quickly remind you what that is and what it's good for. So I want to remind you of 2 things that entanglement is good for. So, you know, when you first hear about entanglement, you imagine some very simple bell pair of qubits, right? There might be, I don't know, up, down, plus down, up, or something, and that's entangled. But when entanglement generally becomes useful is when you have a large number of quantum degrees of freedom. So for example, suppose you have some spins on a lattice, for example, and the interactions between these spins are local. So for example, the Hamiltonian is maybe it's some nearest neighbors, si.sj, something where these are spins. But it could be anything. And local means, 10, some for example, some finite range interactions. So you can prove with some assumptions that when the interactions are local, if I take a region, this region here, and I ask what's the entanglement in the ground state wave function of all the spins in here with all the spins outside, you get what's called an area law, although in this case it's more of a perimeter. And so the entanglement goes like the boundary of this red circle there. And that's saying that, of course, this interaction wants to entangle neighboring spins, right? It wants to make them singlets or triplets, depending on the sign of the interaction. And what this is telling you is that, indeed, that is an accurate picture of the entanglement. Most of the entanglement in the ground state of a local Hamiltonian is due to the short-range interactions entangling nearby degrees of freedom. But this is a massive simplification because that's not true for a generic state. If I take a generic state of these spins, so there are 2 to the n spins, right? So there are 2 to the n states. And so n is the number of spins. And so if I wanted to find the ground state, I would have to diagonalize a 2 to the n by 2 to the n matrix. However, almost all of these 2 to the n states have very long range entanglement, meaning that if I take a typical state in the spin Hilbert space, this spin in the middle will be strongly entangled with some spin over there. And so there's a theorem that cannot happen in the ground state of a local Hamiltonian. And that means that these local Hamiltonians live in some very small so the ground states are some very small subspace of all the quantum states that obey area laws. And that's a very useful thing if you're trying to simulate these ground states. Okay, that's something an entanglement is used for, right? So it tells you what kind of states arise as ground states of local theories. A second thing that's useful for is diagnosing the existence of emergent gauge fields. So this, for example, let's again imagine this kind of spin Heisenberg type Hamiltonian. There's not a gauge field in sight, okay? But it can happen that if the interactions are frustrated, that at low energies, the low energy description has an emergent gauge field. It might be a Z2 gauge field, okay? But there's some gauge theoretic topology in the ground state. It turns out that this phenomenon can be diagnosed with something called a topological entanglement. And so what the topological entanglement is, it's a correction to this area law. So there's an area law, and the topological entanglement is a certain constant subleading term. And how would you extract the subleading term in an interesting way? Well, something you can do, so this is by Kitaev and Preskel and Levin and Wen, you could consider various regions like this, right? And so you see the regions, the area of the region A minus B or C minus D, they're made so that in this combination of regions, the length term cancels out, right? So these are regions that if you add and subtract them, you cancel out the length. But crucially, these regions have different topology, right? This one has a hole in the middle, and this one is disconnected, okay? When you have an emergent gauge field, there are sort of Gauss law constraints on the ground state. And what these Gauss law constraints mean is that all of these different sort of links, different degrees of freedom that you're partitioning, they're not all independent because they're global Gauss law type constraints. And that meant that this area law slightly overcounted the entropy. And this overcounting of the entropy is what leads to this subleading correction that you can extract so in this sort of topological way. Okay, so the entanglement entropy also, it knows about the locality. So the entanglement entropy, if I give you a state, and if it's a ground state of a local Hamiltonian, you can deduce that from that is manifested in the state in this area law, and if there's an emergent gauge field, also in this subleading correction. Okay, so entanglements are a very useful thing for characterizing quantum many-body states. All right, so suppose we want to understand the Ryu-Takayanagi entanglements. What kind of microscopic models should we be looking at? And so they're not spin systems, right? That probably. And so the natural class of microscopic models to think about involve large N matrices. And that's because it's been understood for a long time that the simplest microscopic models of holography that actually have semi-classical gravity, okay, so have something like Einstein gravity in them in a semi-classical regime, are large N matrix quantum mechanics. Okay, this could be also a large N gauge theory, in which case just put it on a sphere, take n equals, if n equals 4 super-Yang-Mills is in your mind, just put it on an S3 and expand it in modes, and that's a quantum mechanics. It's a very complicated quantum mechanics, but it's a quantum mechanics, okay? So I'm including quantum field theory on a sphere as complicated instances of large N matrix quantum mechanics. And so, of course, I'm going to consider simpler examples. So, and I'll show you some of these matrix quantum mechanics in a second. So the name of the game is to, can we characterize the entanglement of the ground state wave functions of large N matrix quantum mechanics? And do they have anything to do with the Entanglement formula? Okay. So, right. So ideally one would take, BFSS or some maximally supersymmetric model like this. That's rather complicated. And so my strategy is going to be to start with the simplest possible types of models that have the ingredients of a large N matrix structure and try to solve those. And then we're going to take baby steps towards the big problem. And so the very simplest example, there's actually too simple, but I'll tell you about it quickly, it is understood, and since the 90s, how a single large N matrix can give rise to an emergent one-dimensional space. So let me tell you a bit about that. Good. So now I'm transitioning, so that was the motivation. Now I'm transitioning to specific microscopic models, okay? I want to understand the entanglement microscopically. Right. And so the very simplest model you could think about would be a single matrix. Okay, so M is an N by N matrix, and this is its Lagrangian, right? It has a kinetic term, and it has some potential, and what's meaningful is that there's a trace structure, right? That the interactions have a certain structure. So this has been solved to death since the 90s, but it's going to be useful later to just quickly review something. Because there's a single matrix and it's gauged, so these rotations are gauge transformations. So we can go to the singlet sector. The gauged singlet sector is described by the eigenvalues of this matrix, right? If I can rotate a matrix like that, the gauge invariant data are the eigenvalues of this matrix. And it turns out that if you take this Lagrangian, imagine writing down the path integral for this Lagrangian, go to this eigenvalue description. When you do this, there's a measure that turns up that's called the van der Monde determinant. You can absorb this measure into the wave function. And when you do that, when the dust settles, you find that these eigenvalues, there are n eigenvalues, right? Lambda 1 to lambda n, because they're n by n matrices. These turn out to be non-interacting fermions living in this potential. Okay, so that's not an obvious thing. This van der Monde measure has a minus sign, and that ends up making the fermion there's a wave function. There's a wave function. The ground state is some wave function of these eigenvalues, and it turns out it has to be antisymmetric in the eigenvalues. Okay, and the Schrödinger equation that this wave function obeys turns out to be n non-interacting particles, each one in the potential via lambda. Okay, so all that to say, so what I mean by n non-interacting fermions is that the Schrödinger equation is sum over the eigenvalues, t squared d lambda I squared plus v of lambda I, and that's the Hamiltonian. Okay, summed up. Right, so it's a copy. It's n copies. They don't interact, but they're fermions. Okay, so let's say here's the potential. What's the ground state of fermions? It fills up a Fermi C, right? Because they can't all occupy the same state. And so the ground, you have your n fermions, and these fermions build up this Fermi C. Okay, here's a Fermi C sitting in the potential. What are the low energy excitations of a Fermi C? Well, you have to take an electron close to the surface and move it just a little bit above the Fermi C, right? So you'd take out an electron from here, and you put it in there, right? So a ripple on the Fermi surface is a low energy excitation. So you can show in this model, this was shown in the 90s, that these ripples bounce back and forth in the potential obeying a one-dimensional, a 1+1 wave equation. Okay, so these density fluctuations obey a 1+1 wave equation. And so that's your emergent space, right? This model had no space that you started with, only time. It's just a quantum mechanics. But the low energy physics is given by a 1+1 dimensional wave equation where the space, the eigenvalues sort of built the space for you. And then crucially, the dynamics in this space is local, right? And so this is an example of how a matrix can build a space for you, a one-dimensional space. So then you can ask, how do you see? So this 1+1 dimensional wave equation, which is local, has a certain, the locality of this equation is embodied in a certain entanglement entropy. So in 1+1 dimensions, a massless wave equation gives you a logarithmic entanglement, right? So if I take a region in a 1+1 and I calculate the entanglement of some interval L, I get log L over epsilon 1/3. It's the entanglement entropy, and you need some cutoff because the entanglement is logarithmically divergent. And so, but there's a lot of entanglement because there's a lot of entangled modes. All the momentum modes are strongly entangled across this cut. So how does the entanglement in the ground state of the eigenvalues know about this emergent locality, right? So we calculated it a few years ago. And actually, it turns out Schmidt-Das had actually already done this calculation 20 years before. We used some techniques that had been invented in between, but it's basically the same calculation. It's a really nice, very prescient paper by Das. Actually, it's very impressive. I mean, he was calculating entanglement entropy in string theory, before most people knew what entanglement was. Okay, so it's a very, very nice paper. And so it turns out that you can use this wave function of the eigenvalues, and you can calculate its entanglement using conventional many-body methods, okay, because it's just a many-body system, right, of n eigenvalues. And we got this log. We recovered the log with the cutoff now, and the cutoff ends up being related to the depth of the Fermi sea. So that depends on n and on the potential. And so you get a microscopically finite entanglement entropy from these n eigenvalues that captures the emergent locality of your space-time. Okay. All right. So this is yeah.
Sean, can I ask something?
Yeah.
Is the subspace in the original matrix model in the space of this eigenvalue, is the subspace well defined that corresponds to the region of certain
wonderful.
Space?
Thank you. This is an excellent question, which maybe I should have had a slide on it. And this is a very good question. Let me tell you how it goes. So the question, let me repeat the question first. I think the question is, so in the spin system that I showed you before, there were a bunch of spins at different points, right? And when you partition space, it's clear what you're doing, right? You have this, the Hilbert space is a tensor product of the spin here and the spin there. And so there's a clear factorization of the Hilbert space. Now let's say I have let's do one particle quantum mechanics. There's a space X, but the particle could be anywhere, right? It moves around. And so when I partition space into, let's say, this side and that side, that doesn't naturally come with a factorization of the single particle Hilbert space. Is this your question? I think it was, right?
Yeah, exactly. Yes.
Yeah, good. So good. So for example, in fact, it's the direct sum, right? So a general state of the particle is some psi of x, right, in the position basis, and I can write that as a sum of the integral of a of x less than some x0 plus x bigger than x0, and that's not a product. That's not the structure that you need to define entanglement. Okay, so this is, I mean, actually, people have been doing this, as you said. Oops, sorry. So Das was already doing this. I mean, people have been doing this for a long time. It recently has the name target space entanglement. But it goes, the way I think about it is as follows. So what you have to, okay, so the simple thing you can do is second quantize your system, and then you have a field, right? You can build a field. You can build now a quantum field by summing over the eigenvalues. So you do something like this. right? So you solve your Schrodinger equation. I'm going to justify this in a second, but just tell me a simple-minded thing you can do is solve your Schrodinger equation, find all the energy eigenstates. Those are psi lambda of x. So these are wave functions. They're not operators. They're wave functions. And then to second quantize the system, you define an A dagger operator that creates a particle in that state. And then you sum over all the states. And now you have an operator that's also labeled by X. And that's the quantum field. And the Hilbert space of these are now operators labeled by X. And so their Hilbert space does factorize. Okay, so what did you do? To do this is that you have to allow a Hilbert space that has a variable number of particles, right? So to be able to just a quantum, the original Hilbert space had only one particle. If you embed that into a Hilbert space that has a variable particle number, you can define the factorization. And let me show you a low-tech way to see that. So what you do, so one way you can do it is, right, so you have your regions and you're going to cut it, and there's two, let's say there's one particle, and there's two possibilities. The particle could be on this side, or the particle could be on that side, right? And so I'm going to define a reduced density matrix that lives in a bigger space where on this side, there's 0 or 1 particles. Now that's not a subspace of the original Hilbert space. And let me give you a sense of it. So you have your state psi, that was psi of x, right? That's in the position basis. So I split that up into the integral of x less than x0, psi of x, and x bigger than x0, psi of x. I can any state. But now I'm going to embed this in the bigger states where I think of this as a particle at x in x less than 0 and no particles in x bigger than x0. And this state I now interpret as a particle in x bigger than x0 times no particles in x less than x0. So I append it with a 0. And now I have a tensor product structure that you can use. And to show this sensible, what you would get for the single particle, the entanglement entropy, is the probability that the particles here, log p, plus the 1 minus p, log 1 minus p. And where p is the integral of psi squared over the region. Right, so that was probably a little fast, but I'm just trying to, the essential point is that you need to, when a state doesn't factorize in the way you want it to, the Hilbert space, the natural thing to do is embed it into a bigger space, and the bigger space and then factorize the bigger space. And the bigger space in this case is a multiparticle space. That's the main point. And it's very natural to do that. Yeah, sorry, go. I'm sorry.
Yeah, I have a confusion here. So suppose I want to lift this wave function to a multiparticle state, right? So I could say that the expectation value of psi, the field operator in this multiparticle state, in this Fock space, should be exactly the wave function, right? But then there are many such multiparticle states which I can construct, which will reproduce the same as an expectation value. Suppose I take this point of view. So there's a very ambiguity in this lifting, right? And so unless there will be some universal answer that comes out.
Let's see, I'm not actually sure there's an ambiguity because, for example, I mean, in this case, the answer for one particle, let's say, I mean, this is the only sensible answer, and it is what you get. So
I understand that, but what I was saying that this is one way that you had a prescription for converting the wave function to an operator in this. But suppose so maybe I didn't. I think you're looking at the operator level, or maybe you're.
But let me say something. Maybe it's something else that might be useful. This entanglement is actually not really very quantum. It's really that there are classical super selection sectors where the particle is or isn't there, and this is sort of there's no interference or anything really happening and so when you have these sort of super selection sectors, you get this sort of sometimes called a classical entanglement, and that's really all it is. It's just counting particles.
So
yes.
So exactly. So suppose I create a coherent state such that the expectation value of psi is exactly reproduced by the coherent state. So the one particle, so this I'm then lifting the quantum mechanics problem to a coherent state problem. It's a multiple Fock space in the Fock space is big. So now, irrespective, there are many coherent states that can reproduce this expectation value. The question that I wanted to ask is, if you compute the entanglement entropy, would it be the same?
No, but it's stronger. It's not about making up a state that reproduces the expectation value. It really has to be a embedding of your original state in a Hilbert. So it's a state to a state, right? And so there needs to be some sort of, and I don't think there is, some sort of canonical embedding of the
so I understand. You are making some canonical embedding, but what?
So for example, let me. But it's not about matching. I mean, matching expectation values is not enough. So for example, I wrote before, right? Exactly. So look, this second quantized map is you write down an operator of X, which is a sum over the single particle eigenstates, lambda dagger, single particle wave function. Okay, and so in this language, your physical state is just a dagger lambda 0 on 0, right? The ground states. You have the ground state of the system is that where this is the creation operator for one particle in the ground state. Okay, and that's the only way you're going to embed the ground state into this space. But this space is a much bigger space because it also has states where you create an excited state. And this state didn't exist in your original Hilbert space because you only had one particle.
Yeah.
Right. So. But it's a state that you're writing down. I mean, I don't know.
No, I understand. So you're just creating. So now you're creating the state by acting the psi of X. You are making it an operator statement. I understand now. Mm-hmm. So this psi of X acts on the vacuum to create your multiparticle state that corresponds to the canonical wave function. I see. So this is So this construction. So this would be independent of your choice of basis or.
Yeah, I think so. I think so.
Okay.
Yes, I think so.
Okay, thanks.
No, it is an important point. So that's good.
Sorry, can I just ask one small question?
Please.
Yeah, please. Maybe you just explained it. I kind of didn't quite get it. Here, when you are talking about this target space entanglement in the emergent theory, is there any natural interpretation of that in terms of the matrix degrees of freedom?
The matrix, yes, yeah. It's the entanglement it's the target space entanglement of these eigenvalues. So the eigenvalues take values, right? Lambda is every single eigenvalue takes a value between 0 and infinity, right? They take values, and it's the entanglement between all the eigenvalues that are less than some value and all the eigenvalues that are bigger than some value. So,
I thought the emergence of this 1D space was mostly from this density fluctuation, but you're saying that I should think of the eigenvalues themselves as living on 1D.
That's the non-trivial. No, good. This is exactly what we want to do. So the objective is to understand what partition or factorization of the matrix Hilbert space corresponds to the emergent Hilbert space, precisely because there are different variables, right? The natural local variables in the emergent space are these density fluctuations. Yeah, you're absolutely right. And these eigenvalues are something else. But we're trying to find the locality of the density fluctuations in the original Hilbert space.
So you're going to answer that question.
Well, I'm telling you in this case in this case of a single, what I said so far is that for a single matrix, the way it works is that the target space entanglement of the eigenvalues captures the the collective the partition in the original space. But that's not guaranteed to always work. Yeah.
Okay. Yeah. Thanks a lot. Yeah.
No, good. And so how that might generalize to higher dimensions is what we're going to come to in 1 minute. Yeah. Thanks. Please. I'm very happy to take the questions. So keep them coming. That doesn't matter how far we get. All right. So now, however, eigenvalues are really not enough. And in more sort of mature, sophisticated models of holography, you have multiple, the eigenvalues are like branes. They're also strings that stretch between the branes. For example, in the original ADS-CFT, you take these D3 branes and you put them on top of each other to make a stack, right? And when you do that, these off-diagonal modes that connect branes are also very, very important. And so we have to understand how to deal with those. And one way of saying this is you have more than one matrix. And if you have more than one matrix, let's say an X and a Y, so two matrices now, two matrices don't commute generically, right? And so that means that even if you diagonalize one of them, the other one will not be diagonalized, and it will also have some off-diagonal modes. And now what are you supposed to do with these off-diagonal modes? Okay, so there's a qualitative difference once you go beyond one matrix, which is that you need to deal with the actual matrix structure. One matrix is barely a matrix because you can diagonalize it, and the eigenvalues are just like particles, and you're back to doing multi-particle physics, which we've known how to do for 100 years, right? But when you go beyond one matrix, you really have to grapple with these off-diagonal modes. Okay. So the starting point here is again TFR and Shimida's paper, and so they noted they said the following was the point that we got inspired by. So suppose you have a bunch of matrices X, Y, and Z, let's say 3 matrices. So the way these matrix quantum mechanics work is that even though there's no space, there is a sort of proto-space in that the matrices in the matrix quantum mechanics often end up being in correspondence with dimensions of space. So in the case we just saw, there was one dimension in n equals 4, for example, these 6 scalar fields are related to the S5, naturally wants to live in that space. So in general, I think this is a nice point, a nice observation. Suppose you define a cut. So imagine let's just do two matrices. So suppose you imagine you're going to have a 2-dimensional space and you want to cut it along some line. You want to partition your emergent space along some line. This line is defined by some equation, f of x, y equals 0, right? That defines your cut, all right? So associated to that, there's a natural matrix F where you take the x and y's and you replace them with matrices x and y, and then you get f of big X and big Y, right? That's now a matrix. This is one matrix, and one matrix you can diagonalize. And so what they said is you should diagonalize, you should take the equation for your partition, diagonalize the corresponding matrix, and then partition the eigenvalues of this matrix into f less than 0 and f bigger than 0. And the proposal is that corresponds to this cut in the space. So it's a natural generalization of the 1D case.
But the
right?
function is not unique. The matrix function
that's
is
correct.
not unique.
Well, sorry, what's not unique is
because
the ordering.
ordering ambiguity.
Yes, that's correct. So I don't have anything to say about that, but we're going to consider simple cases where there is no ordering ambiguity. But absolutely, yes, that's absolutely right. That's right. And actually, this point should be, someone should look at it, actually. It's a good point. Right. Well, actually, I mean, yes, very good. So yeah, I'm going to consider cuts that don't have an ordering prescription. Or, yeah, sorry, we'll come back in a minute, actually, to that point. Good. So, but nonetheless, it's a nice thing that if you have a codimension 1 surface in your space, that corresponds to one function, and that gives you one matrix which you can diagonalize. All right, so that means, very good. So that means you take one of your matrices. So let's say that, so let's start, for example, with just x equals 0 being, so that there's no ordering ambiguity here, right? Just take one of the matrices. And so that's like a cut through a hyperplane through your space given by x equals 0. So then you should diagonalize x. Okay, but y is clearly not diagonalized. Right? So, and now the claim is you should order the eigenvalues of x and partition them. Now, if you're sort of following your nose in this game, right, that you might think that will induce a block partition of this second matrix, right, in the basis. So the first eigenvalues define a basis for you, and you write down the other, you get a block partition. And it is pretty, following your nose, it's pretty plausible that you should put these on one side and you should put these oscillators on the other side. But then the real question is, what are you supposed to do with these off-diagonal operators? Okay. And I think they didn't really answer that question. They said, well, you could put them on one side or you could put them on the other side. Okay. So what I want to talk about now is what we should do with these off-diagonal. So once you have more than one matrix, you have to do something with the off-diagonal modes. Okay. So I want to tell you what I think is a nice story about those guys. So to do that, I'm going to introduce a solvable matrix quantum mechanics with two matrices so that I really just have a model to work with. And I'm going to just compute the entanglement of a geometric partition. And the way we're going to treat the off-diagonal modes is going to be inspired by entanglement and gauge theories. So in gauge theories, there are also links that cross the Wilson lines that go across your cut. And you think, well, what side am I supposed to put those on? And people have understood the answer to that question. And we're going to apply the same logic to these off-diagonal blocks. And this point was previously made in a nice paper by Albion Lawrence and friends. What we're bringing to the table is a really specific model where you can just see how it works. And there's some subtleties which you have to deal with. And so everything I'm going to talk about now is in this paper. I'm going to obtain an emergent 2D area law. And I'm also going to obtain some topological-like subleading corrections. So I'm going to quickly introduce the model. Right, so we're going to have I think it's the simplest possible model with two matrices. As you're going to see, it barely has two matrices. Okay. So what is the word quantum Hall doing here? So what's the essence of quantum Hall physics? So you take some electrons, they're in a lattice, they're strongly interacting with each other, and they're disordered. Okay, horrible system. You apply a huge magnetic field to these electrons, so they all want to go into this lowest Landau level. When you do that, something interesting happens, which is that the electrons become incompressible. Okay, and so the first essence of these quantum Hall phases is that the electrons enter an incompressible phase. You have some trap that's keeping the electrons in place, and then have a huge magnetic field. They form a droplet, and this droplet is incompressible, meaning that if you poke it somewhere, it has to pop out somewhere else. And in fact, for example, Laughlin's Nobel Prize winning paper on the fractional quantum Hall effect has the word incompressible in the title. Okay, it's a very fundamental aspect of quantum Hall physics. And furthermore, these droplets, it's gapped, right? Because it's incompressible, and the bulk is gapped. And it's described by a Chern-Simons. There's an emergent Chern-Simons theory in the bulk. Okay, now suppose you say, well, that sounds very nice. I like Chern-Simons theory. I like incompressible theories, but I don't like electrons in disorder and so on. What this quantum Hall matrix model is, it's a UV completion of this incompressible droplet that preserves as many of the symmetries as possible. Okay, so it's a theorist's UV completion of the quantum Hall effect, right? And so, I mean that in a very literal way. So you can think of this model as a minimal microscopic realization of quantum Hall physics. And the essential point is that there's a natural way to discretize area preserving diffeos. So a incompressibility, right, means that if you poke it here, it has to pop out here, and the area has to be preserved. And so the natural symmetries, the natural group that acts on a incompressible system are area preserving diffeos, right? You move the system around, but you preserve the area. As was known since the 80s, the group UN, the limit as n goes to infinity of UN, becomes the area preserving diffeos on a sphere or on a disk. I'm not going to, in interest of time, I maybe won't go into this, but it is true. Okay, so this underlied, for example, early matrix theory, the membranes, right? So that the matrices become the membrane, right? And the diffeos on the membrane are inherited from the UN transformations on the matrices. And so this was a sort of Lenny Susskind's point. And so he wrote down a matrix quantum mechanics that had a UN symmetry that as n goes to infinity gave you some incompressible-like physics. And Polychronakos, okay, the problem with Lenny's model was that it required n strictly equal to infinity. It was not a droplet, it was like a plane. And so Polychronakos regulated it. And so now let me write down his model. This is it, it's very simple. So there are two matrices, x and y, and the Hamiltonian is just trace of x squared plus y squared. Furthermore, so the Lagrangian has a first order kinetic term, which means that x and y are quantum mechanically conjugate to each other, component by component. All right. However, the UN, and there's a UN symmetry that leads to this Gauss law. Okay. Now this Gauss law has has a charge k. All right. And right, so this is the sort of natural generator of a Gauss law. And then there's this vector. This vector is not going to play a very big role in what I talk about. It's the reason it exists is that if you didn't have it, this would be a Heisenberg algebra, commutative xy equals a number, and that does not admit finite dimensional representations, right? That's because once you have raising and lowering operators, you just keep going up, right? So you have an infinite dimensional space. What this does is it truncates it. So if you imagine having a Heisenberg, some A daggers, right? So you build a dagger from x plus I, y, something like that. If you raise it a certain number of times, eventually it gets killed. And that this is a projector that stops the raising going beyond a certain point. And that's what makes the droplet finite size. Let me not go into it. Just believe me, it's not very important. It doesn't really do anything. Okay, so this is the model. And in the same, as you see, this was a busy year for this model. Hellerman and Van Ramsdorff just wrote down the ground state wave function of this model. It's a bit complicated, but then Caravalli and Sakita wrote it, among other things, wrote it down in a very nice form. So I'll just tell you about that. Okay, so you've got this Hamiltonian system for two n by n matrices, and it turns out that the nice way to write it down is to parameterize your system by diagonalizing. So you diagonalize one of the matrices. So remember, x and y don't commute quantum mechanically, so the wave function is just a function of x. So you diagonalize one of the matrices, and you also rotate this vector. And then the wave function takes this form. There's a wave function for the eigenvalues of x. And remember, diagonalizing x is something we want to do to make this vertical cut. So this is a nice representation. This thing is an overall phase that corresponds with the charge k under this Gauss law. And then there's also some wave function for the vector parts that's not going to be important. This wave function may be familiar from single matrix quantum mechanics. So we just know the state. Yeah.
So can k here be an arbitrary number, or is there some quantization?
It has to be an integer. Yeah, positive integer.
Okay, but how do we see that?
Yeah, it actually follows from the representation theory of this this algebra.
Okay.
Yeah.
Okay. Thanks.
Yeah, it does have to be an integer. You can. Yes. Very good. Good. So then, all right. So yeah. So. Yes, fine. I think we're not going to get too much technical stuff, but that's probably a good thing. So this wave function factorizes, and so it turns out that there are two contributions to the entanglement giving a cut. So the first, I'm going to go back. So the first contribution here just comes from the eigenvalues themselves, right? There's a wave function for these eigenvalues, and so if you cut them, that gives you an entanglement exactly the same as in the single matrix quantum mechanics. Okay, so there's a collective field contribution that comes from fluctuations of these eigenvalues. And physically, we're going to see this corresponds to correlations due to a chiral boundary mode that's going around this droplet. But there's what's new from having two matrices is that there's a gauge theoretic contribution that comes from the fact that these U's, the gauge transformations also get partitioned. So we have this matrix, as we imagine block partitioning the matrix, then the unitaries also get block partitioned. And for example, this unitary here, so let this be U, and let this be Y, let's say, or one of the matrices. This U left acts here, but it also acts there. And this U right acts here, but it also acts there. And so these off-diagonal guides. So you have a gauge group that acts on the whole matrix. We partition the matrix, and there's a natural partitioning of the gauge groups, which sort of act on the two sides. But there's but these gauge transformations also act on these off-diagonal modes. And this is just like in a lattice gauge theory, as I'll say in a second. The link that goes across your cut is acted on is bifundamental under both sides. So these off-diagonal modes are charged under gauge groups that want to live on both sides. So we started off with a UN. We started off with a UN, and we partition the eigenvalues, so that naturally gives you a break to a UM cross a UN minus M. But these off-diagonal modes are acted on by both of these, okay? And that correlation gives you another contribution to the entanglements, as we'll see. And so the picture that we're going to get to is the following. So you have the eigenvalues of X. The eigenvalues of X don't commute with Y, so they're delocalized in the Y direction. And so these gray lines you think of as like eigenvalues of the X matrix. Okay, they have their own dynamics, right? They're fluctuating, and so how high this line is roughly how many eigenvalues there are at that point, and that can fluctuate a bit. And when that fluctuates, this droplet changes size a little, its boundary changes a little bit, and so there's some contribution. And then this is the blue lines that the entanglement cut that we're trying to define, right? And so there's some. So there are two contributions from the entanglement, one from the eigenvalues fluctuating themselves, and that is a sort of a boundary effect. And this gauge theoretic thing I was talking about is that there are certain off-diagonal modes of the Y matrix that's not diagonalized that live on that are associated to eigenvalues on opposite sides of the cut. These are the off-diagonal Ys. Or rather, there are gauge transformations that sort of act across the cut. And right, and these are also going to contribute to the entanglement. And the entanglement is essentially going to be a counting problem, which is essentially the number of gauge transformations that act on these off-diagonal blocks. Okay, so let's see. So this is meant to look like strings cutting, going across the cut. What they are they're modes of the matrices that are acted on by gauge transformations on both sides. As was okay. So let me see. Oh wait, sorry. I just realized my computer. Wait, what time is it?
6:24 p.m. here, so it should be 2 p.m. for two, almost 2.
Okay, and so I have like 5 minutes, 10 minutes, something like that.
No. Well, you can take a little more time. I mean, you can take 10, 15 minutes maybe.
Okay, 10. Yeah, okay, good. I don't want to overrun too much. So yeah, 10 or 15. Okay, very good. Okay, so there are these two separate contributions. So first, I'm going to think about the eigenvalues. Right? I showed you a wave function for the eigenvalues. This calculation is very similar to calculations that people already did, but we did use a new method. So I'd like to show it to you. I think it's a little bit nice. So let me go back. So just to be clear what I'm talking about this part of the wave function here. The eigenvalues have some wave function, and I want to calculate the target space entanglement in this wave function. Because this K in general is different from 1, these are not free. It turns out these are not just free fermions. You can't use the free fermion trick in general. So we did it a bit differently. And so you can define this collective field N. So what is this? This is N of X is the number of eigenvalues close to X, right? So this is a function that has a delta function on each eigenvalue, right? And so if you integrate N of X between 2 points, it counts the number of eigenvalues between these 2 points, right? It's the density of eigenvalues. And then in the large N limit, it becomes a smooth function. Okay, so N of X is how many eigenvalues, right? So here are the eigenvalues that I'm summing over. And N of X, again, is the sum of delta functions of each eigenvalue. In the large N limit, it gives you some distribution, it gives you the eigenvalue distribution. All right. I'm going to write the wave function. I can write this wave function in terms of N of X instead of the XAs. Like this. So for example, we had e to the minus sum over a xa squared, right? That was one term in the wave function. This is just completely equal to e to the integral n of x squared dx, right? Because when I integrate over n, the delta functions just turn into this sum over a, right? And so I can think of this as a wave function, not for the eigenvalues, but for the eigenvalue distribution. And so this term in the wave function becomes e to this term, and the prefactor, which was x minus x to the k, I write that in the exponent as e to the k log x minus x, and I can again write that in terms of the eigenvalue distribution like that. Right? And so I can think of the wave function instead of a wave function of eigenvalues.
How do you handle the singularity when x1 equal to x2? You put a
Yeah, this is very mild. It's integrable, so it's not going to matter.
Okay.
Yeah, thank you. Right. Yeah. So this is a well-defined integral. So now I'm thinking of the wave function as a wave function, and the eigenvalues were ordered. Actually, I'm going to order because you can use the unitaries to order the eigenvalues, and so I'm going to put all the ordering ambiguity into the unitary matrices, and the eigenvalues are going to be ordered. So that's important because this n of x is invariant under permuting. It doesn't care which eigenvalue is which; it just counts how many. All right. So there's a wave function for the eigenvalues, and so this wave function, if I calculate, it's how likely I am to find an eigenvalue at n, I would look at mod psi of n squared, and so this quantity at large big N is very strongly peaked on a certain distribution. So this wave function is basically classical. In this collective field is a classical variable at large N. And this wave function is very strongly peaked on this Wigner semicircle. Right? So I think of, essentially as N goes to infinity, this probability distribution is basically a delta function on N of x minus N0 of x. Right? There's a certain distribution of eigenvalues that overwhelmingly dominates the wave function, right? It's not a partition function, it's a wave function, right? And it's strongly supported on a certain distribution, which is this Wigner semicircle, right? That looks like this, has some radius that depends on n and k, all right? So there's no entanglement yet, right? This is just a classical dominating saddle. To understand the entanglement, we can look at fluctuations away from this saddle. So we just look at values of the collective field close to this saddle, and you expand the wave function, right? So the wave function is strongly, just imagine a wave function that's strongly peaked, but of course it has some fluctuations about its peak, and that's what these are. And if you look at the wave function close to the saddle, you find that it's this Gaussian wave function for these fluctuations. It turns out it's negative. It looks like it might not be normalizable, but it's actually negative. So when you actually evaluate this, it's negative. Okay, and so this is a Gaussian wave function, and Gaussian wave functions are something that we know how to calculate the entanglement of, with some work. And so we just calculated the entanglement in this wave function, corresponding to splits. Of course, also n of x is naturally split into x less than x naught and x bigger than x naught. And we found so we got the entanglement, and it's finite, right? But this collective field sort of threw away the discreteness. But it turns out that it's there, that when you do a Fourier expansion of these fluctuations, it's truncated at n. That's just a known thing. And so the entanglement entropy gets cut off. And so we got this answer very similar to the previous log, where L is the length of this cut. L is the length of this blue line. And what this actually, this might be familiar to some of you. So if L is the length of this line, this is the sine of the angle on the circle. And so this is actually 1/6 log n sine theta, where theta is some opening angle in this circle. And this is the entanglement of a CFT, right? 1 + 1 CFT on a circle. The entanglement entropy of an interval is this, and which we're getting here. And it's 1/6 because it's a chiral mode. It's not 1/3, you get 1/6. But it's completely finite, and there's an n. It renders it finite. Dot 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 mean order one terms. And so this matches a calculation in Chern-Simons theory. Okay, except we have a cutoff. All right, so we calculated that bit. That was the sort of, I mean, maybe less novel, but I think we used a nice method. I feel this collective field method might be useful in many body systems more generally. All right, but now what about the gauge theoretic bits? Okay, so I think that's the. So now I want to quickly tell you about that. So let's go to. I'll just want to give you the intuition for it at least, and that comes from lattice gauge theory. So in a lattice gauge theory, so that you have a lattice and there are gauge fields that live on the links of this lattice, and the gauge invariant observables are Wilson loops that may have a closed line of these guys. Say you want to cut it like this, right? What do you do with these kind of Wilson loops that just go through your region, right? Your Hilbert space is naturally written as a sort of a Fock space of Wilson loops. Those are the gauge invariant quantities that you can create. But how do you partition? I mean, the interactions are local, so it is reasonable to hope that there's some sensible notion of local entanglement. But these gauge invariance is at odds with that. Okay, so one thing you can do is just throw them all away, and you'll calculate something. There's a well-defined entanglement, but it's a bit impoverished. It doesn't know about a lot of the interesting things. So the simplest thing you can do, there actually have been by now various ways of dealing with this situation, and they all give you, I think, the same physics. The simplest one is that these links that you're cutting, so that there's a gauge there's sort of a holonomy or a gauge connection that lives on this link. The idea is you're going to embed your state into a bigger space where you double that link and you associate one copy to each side. But when this uplift into this bigger space where you double the Hilbert space on this link, you have to do it in such a way that the uplifted space still obeys Gauss's law. So it's crucial. It can seem in some of these discussions about entanglement entropy and gauge theories that people are breaking gauge invariance, but it's not true. The uplifted space has to obey Gauss's law. So the gauge generators acting on this bigger space have to give you 0. And the way it works here is that in many simple cases in lattice gauge theory, is that these 2 copies of the holonomy that you introduce have to be entangled in the uplifted space. So you sort of duplicate something, but then Gauss's law requires you to kind of glue it back together again. It's forced on you by Gauss's law. And so the uplifted state that you make, right? So you have some ground states, right, of your lattice gauge theory. You lift that to some bigger space where you include some pure gauge modes that were not there in the original states. But in this state that you uplift to, when you insist that G annihilate, the Gauss law annihilates the states, it forces these U's to be maximally entangled in many cases. And so you get an extra contribution to the entanglement from these U's that you introduced. And you really were forced to do this if you wanted to define a factorization of your Hilbert space. And so actually you get an extra area law, right? Because it goes like the number of links that you cut. And for each link, you get the entanglement is the logarithm of the dimension, because it's maximally entangled, it's the dimension of the space that lives on each link. And so you get a universal contribution like that. And what's nice, because these things are maximally entangled, in this circumstance, entanglement is literally a counting problem. It's the dimension of the space, right? Normally, entanglement is not always a counting problem, but I mean, it depends it's a question of definition. But when something is maximally entangled, then all the states are entangled, and the entanglement is just a dimension of the space, which is a counting problem. And so that's going to connect with this Hardy-Ramanujan story in a minute. Okay, almost there. I'll tell you in a minute how we're going to partition. Yeah. So So in our case, we have these U matrices that are basically pure gauge in the full theory. But I want to argue that when we partition the system, in the same way that we have to include some pure gauge modes here, we should include some of these SUN rotations in our case. To argue how we do it, let me make another analogy with Chern-Simons theory. This is following Donnelly and Frida. So imagine Chern-Simons theory. So here's your, and I'm going to be in a gauge where A0 is, that, yeah, I'm going to set A0 to 0. So here's the Chern-Simons Lagrangian integrated over a two-dimensional space, and there are two components of A. Now, let me just split that integral as an integral over one side. I wanted to find a phase space that corresponds to just one side.
I don't know whether it happened with me, but you were like offline. You went offline for a minute.
Okay, let me see. What was the last thing that you heard?
You were talking about this partitioning of the second point, actually, that you're explaining this Donnelly-Friedel result, actually.
Yeah, very good. Okay, so let me. So imagine in Chern-Simons theory, the Lagrangian is this integral over space, but I can write it as a sum of the integral of one half plus the integral of another half. And now suppose I want to quantize just one half by itself. If you do that, because in Chern-Simons theory, it's only gauge invariant after you integrate by parts. If you have a boundary, the pure gauge modes that act on the boundary don't leave the action invariant, and they have a phase space. So if you consider a pure gauge mode that doesn't vanish on the boundary, there's an effective Lagrangian for these modes. I just take these modes and I plug them into the Lagrangian, and I get a non-trivial kinetic term for them. That means they have a non-trivial phase space. And in fact, this is precisely almost a chiral mode going along the boundary. And so, so pure gauge modes that don't vanish on the boundary acquire dynamics when you only consider a subset of the system. In the matrix case, what we're going to do is there's a Lagrangian that I didn't write down before. The Lagrangian is trace z dagger z, where z is x plus iy. Sorry, z dagger z dot. So I'm going to take this trace and I'm going to split it up into two parts, where theta is some projection matrix. Okay, so this is true for any theta. I can always do this, right? I'm going to split up the trace into two parts. For those, if any of you might have played with non-commutative geometry in the past, it's very natural to associate integrals and traces. That's how it goes. All right, so I'm going to split up. I'm going to partition the kinetic term of the Lagrangian into two bits. And what this theta is going to be is a projection onto the lowest m eigenvalues of x. Remember, we diagonalized x. Okay, I'm going to order its eigenvalues, and the lowest m of them then define a subspace, and I can define a projection onto that subspace. All right. So this will be the last slide, I think, that I'll go through in any detail. So what you do this is the projected Lagrangian. This is analogous to the Chern-Simons Lagrangian on just half of the plane. So you get some kinetic term for the eigenvalues, that's fine. But what you also get is a YRL, so X was diagonalized, the Y is in blocks, and these blocks are the off-diagonal blocks. And they appear in this partition Lagrangian. Okay. Yeah. So for example, if I sum these two terms, it ends up being a total derivative, and I would just find the eigenvalues. But if I partition the system, these off-diagonal blocks appear in both of them. But it's a bit hard to explain, but they're pure gauge modes. It turns out that the terms that appear here are, I'm just going to say these words. I think it's probably too much to internalize, but hopefully it might be useful at some point, where these U's, these Y's that appear here are actually pure gauge modes. They gauge rotations of some fixed matrix. In essence, it goes like this. You diagonalize X, and then Y has a form where the block here is given by U dagger is by the gauge orbits of some particular classical matrix. Right. And the gauge transformations that act on this classical matrix are analogous to the Chern-Simons gauge transformations that act on the boundary. All right. So these off-diagonal matrix elements are analogous to links. There's a subgroup. So what this construction does is identify a subset of the unitary transformations that don't leave these off-diagonal terms invariants. Okay, analogous to how there's some gauge transformations that don't leave the boundary invariants. So I will skip the details, but what we did is quantize and count those gauge transformations. And when you do that, we got an entanglement entropy. Let's forget this log for a second. That went like the length, right? So the boundary entanglement that I had before went like the log of the length. This was L. But this gauge theoretic entanglement goes like this length. It's an area law in the bulk. And the bulk, so there is, so these matrix, the gauge theoretic matrix entanglement knows about this sort of bulk, two-dimensional bulk that exists in this problem. There's a logarithmic violation, and that is related to the fact that this cut intersects the boundary, okay? Because we also considered cuts that don't intersect the boundary, and those ones don't have logs in them. So this log is not very, at the first pass, we can forget this log. And so there's some end dependence. So this is a completely finite answer. It's UV regular, it's finite, and it's an area law in an emergent geometry. So the gauge theoretic entanglement in this matrix quantum mechanics knows about the emergent geometry, right? And roughly the way that works is that most of the entanglement comes from off-diagonal modes connecting eigenvalues that are very close to the cut. And how many of those eigenvalues are there? Well, there's n of x0. That's the density of eigenvalues at some point. This is the density of eigenvalues close to the cut. And most of the off-diagonal modes come from close to the cut. And they end up going like the density, which is this height. And so that's where the area law comes from. All right. Sorry, that was a bit brief, but let me, yeah.
Here, because maybe I don't remember correctly, but this log NL times L behavior, isn't it also something seen in Fermi liquids?
Yeah, that's right. I was excited for a couple of days about that. I don't know that there's a connection. Maybe there is. I can tell you that it's definitely connected to the fact that it intersects the bound, that this, so you have an object with a boundary and you're defining a cut that intersects the boundary of the object, and it's definitely coming from that, but I don't, that's all like, yeah. Yes, I agree with what you said, but I don't, yeah. I didn't manage to make anything of that. Okay, so to summarize, sorry for overrunning and starting late. Two sins in one. Okay, so we defined a partition in a simple two-matrix model. Remember, it's a funny area of research, right? We're trying to find the question, right? The idea is to what is the partition whose entropy has some nice properties, right? That sort of looks geometric in an emergent space. And we computed the corresponding entropy. There are two contributions that both match what you expect from some emergent locality. There's a logarithmic entanglement from the eigenvalues. So that's sort of a gauge invariant contribution to the entanglement that corresponds to the chiral boundary modes. And there's an area law gauge theoretic entanglement. There's what you'd expect from a bulk Chern-Simons, from the fact that there's an emergent Chern-Simons field living in the bulk. And what we're thinking about doing now is trying to move on to more complicated matrix quantum mechanics that do have some compressible dynamics. So everything, the reason this case is easy is that the Gauss law is really strong. Almost everything is determined by the Gauss law in this system, and there's not a lot of dynamics. So the bulk in particular is purely gauge theoretic. and that made it easier. All right, thanks for listening.
Thanks, Tom, for this great and wonderful talk. Yeah. So we should take questions now. Okay, maybe I can ask something. So, so here, what is the simplest metrics? We know that BFSS matrix model should give rise to gravity or emergence of gravity in this, or even some simpler versions of it. But then the notion of partition itself is a bit complicated because the area is supposed to be the operator or something like that. So, I mean, there's no land.
Yeah, so it's true, right? Let's see. No, but I mean, in principle, this prescription, this Dazedal prescription, could be applied there. I mean, I think the trouble is that we don't know the wave function. So I mean, it's certainly a much more quantum wave function than this one, and so the problem. So I think, yeah. So what we're trying to do here is disentangle the conceptual and the computational difficulties, because there are, I think, these conceptual. I don't think there's anything conceptually distinct between. Okay, there's a few. It has fermions in it, but I don't think there's anything that conceptual. At least there's one more step which is this compressible case that we're thinking about. So there's like a simple 3-matrix model that's compressible and so on. Not yeah, I think the BFSS. Okay, I agree. There are conceptual and technical problems with BFSS. I think the conceptual ones can be tackled in simpler models where we do know the ground state. In BFSS, we just don't know the wave function. So that's a big difficulty. Another question is, what is the simplest model that has gravity in it? I'm not sure actually. So yeah, I'm not sure. So you should need that I think that would be quite an interesting question actually, whether you really need to go all the way.
Then I have one maybe a little bit unrelated question to the talk, but somewhat connected with the gauge theory discussion. Suppose you have a non-commutative gauge theory. How will you conceptualize computation of, or can you give a notion of?
Yeah, it's the same. Good. This matrix quantum mechanics is a non-commutative gauge theory in disguise, actually. So it's really you can this entanglement I've defined. You can equivalently it is equal to a notion of entanglement in a non-commutative Chern-Simons theory. That's so this UN, right? I talked about this map. Actually, so this UN, and the way it's quite nice. This UN becomes two things. It becomes the area preserving Diffeos, but it as n goes to infinity. But it also becomes the local U1, right? And if n is finite but large, it becomes, so when UN n very big but less than infinity, this U1 becomes a non-commutative U1. And you get a non-commutative Chern-Simons theory. So the finite, exactly. The finite n large but finite is a non-commutative gauge theory. They're just equal.
Okay, I see. Okay, let's any further question? Okay, so if not, then let's thanks on and I end the recording.